I got the Blarg APU hooked up into VSPC, threw away all of the SNES 9X APU, but I figured something out. The VSPC tool had an option to enable or disable the echo, and there was no real feature to do that in the Blarg APU. Once again, I'm talking about the GME APU. The SNES SPC APU seems to be more updated, so it actually might have this feature. I don't know. I'd have to look into that. But before I go into that, this is probably one of the last things I'll do. I can maybe build with the newer APU, which is the SNES underscore SPC. Did figure out how to, with the GME APU, disable or enable echo. And here's what I figured out. In the SPC underscore DSP.cpp, there's this echo buffer, echo underscore buff variable, and there's a place right here that, line 610, where if I comment these two boys out, I can disable the echo buffer. And I'm going to show how that sounds with and without this commented. And then most importantly, I want to talk about what the memory looks like when the echo buffer is using a portion of memory, because at first I was really shocked. I didn't know what was happening when I was listening to a Kirby song, and then I realized, oh my god, that's the echo buffer updating. So on this left one here, this is the one after I commented this out. So let's play the one on the right where I have it stock, with the echo enabled. So you heard the sample play. My SPC program will just play the sample, and then up here it'll just be in a tight loop, as we can see, but it never actually does anything. It'll just be looping. So what I do is, if I hit the U key on my keyboard, as we see in the source code, SDLKU, I'm going to turn on the echo, enable it in the flag. I'm going to start my echo buffer at 5,000 hex, which is 50 times 100 hex. I want a delay of, I think this is the max delay time, which is based off of I don't know how many millisecond intervals, 16 millisecond. I'm rushing, let's slow it down a little bit. 16 millisecond intervals, which 16, I can go up to 240, which should be 16 times 15, so let's check that. Yep, 240. I'm sorry, did I say 140? So I'm delaying at 240 milliseconds. I have a feedback of 40 hex, which is right in the middle. If we look about the feedback, it should be up here. You can do negative phase inverted feedbacks, or all the way up to 7F, which would repeat the echo almost infinitely. And I set my volumes to max, and I initiate the sample. Actually, this should really happen before the sample gets keyed on. This is just the filter. If you don't turn on the filter, then you won't even hear a sound. So I think this is an identity filter, where this one's 7F and all the other ones are 0. Okay. By identity, I meant the same sound as the original. I don't even know if that really is the identity. So anyway, I'm going to hit U, and there it is. Great. When I comment these two lines out, this will be the result. I'm going to turn on the echo, and as you can see, the echo's been disabled. So that's how to disable the echo on the entire DSP. And then if we go down to 5,000, which is where I have my echo buffer set to be. See it here doing. So you see all this memory's kind of doing stuff. Alright, you see all these values just kind of swimming around, but they're not color coded. Yeah, that's the echo buffer. It would be a very smart idea to color code it with a new color. I'm thinking yellow, but it's like, why not? So I'm gonna try to color code that. That'd be cool. Okay, I added to vspc report.h a new report echo mem command, which will output a yellow color, which is incidentally a combination of red and green. The way these report macros work is that, well, let's talk about the regular memread one. After it does this crazy math, it adds 2, and that's the part that we care about, because that means I want to talk about the blue component of RGB colors. And then this will go on to adjust only the blue component of, whatever address. So we don't have to understand all this stuff. I know I certainly chose not to, but I did figure out the color component, which is really all I needed. Now in mine, what I've done is, since I want to get a yellow, I actually do a loop over R component and G component, just like this, and I just have the IDX plus I for everything. You'll see I add I to it, because of course this would have been a part of IDX in itself, but I separated it like that. The only problem, well, we won't talk about problems just yet, but here is what it looks like. I just echo buffs a pointer into the RAM. I have to subtract its pointer offset from the RAM pointer to get its actual SPC RAM, offset value. And then I do it for all 4 of them, because these are little endian 16s. Now, here's what that looks like. I like it. I'm gonna restart it. I like looking at it. You can see where all the code's being currently executed. Very cool. I want to be able to click these voices and mute them. There's another way that you could obtain a yellow color if there's a memory where a write occurred and then an execute occurred on. Those would also contribute to an exact yellow color, and there would be no way for the user to differentiate between. Oh, did I mention that I figured out the problem with the assertion? The problem was that I was writing to the DSP via the actual F2 and F3 registers, where you really want to actually write directly to the like C++ implementation of the DSP, rather than actually going through the APU, because then there's a conflict between the actual SPC program